My main field of research is, our complex systems. And I develop the mathematics for these complex systems. And these mathematics, these mathematical models, they turn out to be nonlinear, partial, stochastic differential equations. They're rather complicated. And the last few years, I've spent mostly on the turbulence problem. This is a famous problem that was proposed by a Russian mathematician, Kolmogorov, who was one of the fathers of probability theory, and his student Obohov. And I have succeeded over the last few years in developing the mathematics to prove this theory and substantiate it. And now I'm mostly spending my time developing methods so that the engineers can use, this model. The turbulence barrier has been holding back our technology. It's the reason why, we can't get easily in and out of space, and the reason why some flights can be very unpleasant when we encounter turbulence. And if we can develop methods, to solve the turbulence problem in a systematic way, it opens up a new era. And a lot of things become possible. For example, we can probably develop planes that can go between any 2 points on Earth in 2 hours. We can move safely in and out of space. We can probably develop flying cars. And there are a lot of applications in industry where we can apply the solution and make it much more efficient. So it's going to have a big impact. I should say that these methods of these complex systems are many, and we are applying these methods to the migrations of schools of fish in the ocean. We have applied them to geomorphology. This is how rain falls on the surface of the Earth and erodes the Earth and how the surface is formed. We all live in a big fractal, but we don't notice it unless we go up in a plane and we look down. Also, we've applied it to the growth of bacteria, on surfaces or in the body. And I'm also involved in quantum systems to design methods so we can design devices which are light and can operate at room temperature and can be put on satellites. And here at Carlos Teixeira, I've been working in the Institute Gregorio Milan with Luis Bonilla and Manuel Carretero. And they have a very nice model of angiogenesis, and this is how veins grow in the body. And in particular, if you have a tumor, a cancerous tumor, the veins grow toward it and feed it. And you want to stop this and control this growth in this case. In other cases, you want to aid it. And I've been helping them to develop methods, similar methods for complex systems, to understand this model better. I also have a long-standing research with Luis Bonilla. We've been looking at the migrations of schools of fish in the ocean. These can be very complex systems. I have a student in California who's working on the anchovy fisheries, off the coast of Peru and Chile. And we have been applying these methods, to this fishery, which is the biggest in the world. And then I have another student, Jonathan Essen, and Luis has been helping me and Jonathan, to combine what's called highly quantum methods, which describe quantum devices which are of the size of atoms, with semi-classical theory. And if we can combine this, then we can make many devices, detectors and sources. We can put them on satellites and they can operate at room temperatures or higher. And that means that they're much lighter. You don't have to put a heavy cooling system, with them as now people have to do. So that opens, many possibilities.